Okay, today we have Matthew Kroeker. He'll be talking about unavoidable flats and representable matroids.
Okay, thanks, Peter. Yeah, so for those who don't know me, like Peter said, my name is Matthew Kroeker. I'm a PhD student at the University of Waterloo, working with Jim Geelan, and today I'm going to be talking about some recent research we've been doing on this idea of unavoidable flats in classes of matroids. And in order for me to explain to you what that means, we have to start with the Sylvester-Gallai theorem. So I'm sure some of you have seen this before, but the Sylvester-Gallai theorem, very easy to state, just says that every rank 3 real representable matroid has a 2-point line. So this is this theorem really inspires everything I'm going to be talking about today. So I've got a quick illustration here. So I've got the non-Fano right here, one of the canonical real representable matroids. And all the theorem is saying is that you can always find a line like this. So a line that spans exactly 2 of the points in the matroid. And in fact, the non-Fano has 3 of these. So that's very nice. It's a very pretty theorem, easy to state. But we want to ask ourselves how and whether this theorem generalizes or extends. And I think that from the perspective of matroid theory, I think there are really 2 crucial questions to ask here. So so the first one is, what can you say outside of real representability? Are similar phenomena guaranteed to occur in more abstract geometric settings, complex representable matroids in general? And then the second one is whether we can extend this result to higher dimensions. So what I mean by that is, so for instance, could we prove a theorem that says that in a real representable matroid with sufficiently high rank, you can guarantee a 3-point plane rather than just a 2-point line? So let's start with the first one. So when you have a theorem about real representable matroids that you're looking to generalize, usually the first place you look is at complex representable matroids. And this has been done. This is a very classic theorem. It's called Kelly's theorem. And this just says if you're rank 4 complex representable, then you're guaranteed a 2-point line. So Sylvester-Gallai was rank 3 real representable. This is rank 4 complex representable. And so, of course, you might ask whether this rank bound is best possible. Can you go down to 3? And the answer is no. So here's a picture of the ternary affine plane. And if you look at this for a few seconds, you'll see that this matroid doesn't have any 2-point lines. And it's well known that this matroid is complex representable. So that's complex. Okay, so actually this ternary affine plane presents kind of a complication, namely that, you know, maybe things worked out pretty well in complex representable with this Kelly theorem, but when we go to matroids representable over finite fields, things can go really wrong in terms of Sylvester-Gallai. So we can look at something even simpler than the ternary affine plane. We can just look at the binary projective plane, aka the Fano. So I mean, this is one of the most fundamental objects in matroid theory. And where we saw a bunch of 2-point lines in the non-Fano before, we see that those don't exist anymore. So this is a matroid that's binary and free of 2-point lines. So Sylvester Gallai doesn't hold in this setting, and moreover, no matter how high we take the rank, we always have binary projective geometries, and they're always free of 2-point lines. And that's just binary. If you look at general finite fields, things look even worse. In particular, just looking at the projective geometry over GFQ, not only do you not get a 2-point line, but every line has length q plus 1. So it's like kind of anti-Sylvester Gallai, like every line is really long. So the point is that things look really different in this setting, but this is what we'll be talking about today. Now, before I move on, just so long as we're on the topic of going beyond real representability, I just want to highlight one other theorem. This is a theorem of Murty, and it's a little more extremal in nature, but it's for general matroids, which is pretty cool. So to kind of motivate Murty's theorem, if you look at this binary projective plane, of course, it has no 2-point lines, but you'll notice that if you delete any one of its points, then you do get a 2-point line. And this is true of any binary projective geometry. You have no 2-point lines, but if you remove one, all of a sudden you find a 2-point line. And Murty's theorem generalizes what I just said. You take any rank R matroid, any general matroid, and if it has fewer than 2 to the R minus 1 points, then you're guaranteed a 2-point line. So like I say, this is maybe kind of an extremal Sylvester Gallai type theorem, and this isn't really the flavor of this isn't so much the flavor of theorem that I'll be focusing on today, but I think it's well worth mentioning, so long as we're going beyond real representability here. Oh, and also, I forgot to say, Murty's theorem also precisely characterizes the extremal examples in this case. Namely, if you have no 2-point line, rank R with 2 to the R minus 1 points for elements, you're a binary projective geometry. Okay, but now let's move on to that second question I mentioned, namely, what can we say about higher dimensions? So let's start off simple. Let's just ask ourselves whether in a real representable matroid with sufficiently high rank, we can find a 3-point plane. So the first place you look is at rank 4, but it turns out that this isn't quite good enough. I've drawn a pretty easy counter example right here. You just take a direct sum of lines, and so long as both those lines have length at least 3, then all the planes in this matroid are going to have at least 4 points. So rank 4 isn't good enough, but it turns out that rank 5 is, and actually more generally for any k, if you are simple real representable and have rank at least 2k minus 1, then you're guaranteed to find a rank k independent flat, which is pretty cool. This is a theorem proved by Hansen in '65. So Hansen didn't prove exactly this. Hansen proved something stronger, which is that real representable matroids, all real representable matroids have a hyperplane with a co-loop, which is also pretty interesting. And then these other authors, Bonas and Edelstein, came along a couple years later and pointed out in a paper that Hansen's theorem actually implies this theorem that I wrote down. So you have sufficiently high rank, namely 2k minus 1, then you're going to get a rank k independent flat. And I encourage you to keep this theorem, this Hansen theorem, in mind, because this is really the prototypical example of the type of theorem that we're interested in this talk. So this is what Jim and I would call an unavoidable flat theorem. So this theorem, in a manner of speaking, says that independent flats are unavoidable in real representable matroids. Now we saw with Sylvester Galli that things worked out pretty well when we moved from real to complex with Kelly's theorem. So it's pretty natural to ask whether you can prove an unavoidable independent flat theorem for complex representable matroids, and it turns out that you can. So the first people to do this were Barak, DeVere, Wigderson, and Yehudiev. And then a number of years later, DeVere, Saraf, and Wigderson improved on the rank bound from the former paper. So this has been done, and actually, and those papers are well worth checking out. Actually, the second paper I mentioned, they give an alternative proof of Kelly's theorem, which is pretty cool. And then very recently, Jim and I improved on the rank bound a little bit. So we proved that rank 4 to the k minus 1 is good enough for simple complex representable matroids. You have at least rank 4 to the k minus 1, you get a rank k independent flat. Okay, so that's real and complex, but now let's get to what today's talk is really about, which is, of course, matroids representable over finite fields. So we've already discussed in a little bit of detail that Sylvester Galli doesn't work in this setting. We saw Sylvester Galli doesn't work, and so these unavoidable independent flat theorems that we have for real and complex, of course, don't extend. But we can still ask ourselves, what are the unavoidable flats? So can we still determine unavoidable flats for GFQ representable matroids? So I know that I cannot prove a theorem which says that if I take a GFQ representable matroid with really high rank, then I'm guaranteed to find a rank k independent flat. That's just not true. But maybe I could prove something which says that if I have a GFQ representable matroid of really high rank, then I get a rank k independent flat, or something else, some other rank k, some other structured rank k flat from some hopefully small list. So to kind of illustrate what I'm saying, let's just think about graphs for a moment, right? So for a graph, I can't say that a sufficiently large graph is guaranteed to contain a co-clique on k vertices. But by Ramsey theory, what I can say is that in a sufficiently large graph, then I'm guaranteed to get a co-clique or a clique on k vertices. And so we're really trying to take the analogous approach here to prove something analogous to that. And what we actually proved is this. So this is not a theorem for general finite fields, but it is a theorem for prime fields. And what we showed is that if you have a prime p and a positive integer k, if you take a GFP representable matroid with really high rank, then you're going to find a rank k flat, which is either independent or is an affine geometry or a projective geometry over GFP. And so this is our unavoidable flat theorem. And And so the rest of the talk, I'm just going to outline how we proved this. So I'll get into that now, unless there are any quick questions at this moment.
Yeah, I have a question. What happens if you look at powers of P?
I will talk about that later in the talk. So I mean, you're asking about like this theorem for general finite fields?
Yeah, and I assume that you can get the prime projected geometries and the prime affine geometries, and actually things that can, yeah.
Yeah, that's a really good guess. So I will talk about exactly that a little later.
Okay, thanks.
Thanks. Okay, I will move on then. So, okay, so actually, before I talk about our proof, I want to talk about the proof of Kelly's theorem. So Kelly's theorem, remember, is this complex Sylvester-Gallai theorem. And because it's best possible, it really is the complex version of Sylvester-Gallai. And I want to talk about, sorry, well, there's a few proofs of Kelly's theorem, a few known proofs of Kelly's theorem at this point, but I want to talk about how Kelly originally proved this, because our proof draws quite a bit of inspiration from Kelly's approach. Okay, so Kelly used this theorem of Hirzebruch. So what I've written here is not actually the theorem that Hirzebruch proved. Hirzebruch proved something much more abstract and general than this. Hirzebruch's theorem is a really deep theorem from algebraic geometry, but one of the consequences that falls out is that if you have a rank 3 complex representable matroid, then you find a line with at most 3 points. So it's like, this is almost Sylvester-Gallai. It's not quite there, but it's quite good. And Kelly uses this. So Kelly's approach is to contract a point, and then in that minor, by Hirzebruch's theorem, you either get a 2-point line, in which case you win, or you get a 3-point line, in which case you find this flat in the original matrix. Sorry about that. Anyhow, you find this flat in the original matroid consisting of 3 copunctual lines. And you can assume that each of these copunctual lines has length at least 3, and that there are no 3-point lines anywhere else in this matroid. So it looks kind of like this. This one that I've drawn is pretty simple. This is actually just a Fano, but it could be much more complicated. These copunctual lines could be very long, but the point is you're not finding 2-point lines anywhere. And then all Kelly does is, at this point, is argue that a matroid with this structure is not complex representable. And that's the proof. Okay. So our proof is like I say, it's inspired by this. It's going to look pretty different because as it turns out, these matroids, such as the one that I've just drawn, we call these reed geometries. These things can be represented over finite fields. And so you don't get the immediate contradiction like in Kelly's theorem, but what you do get, and I'm about to show you this, you do get a lot of structure. Okay, so yeah, let's talk about these reed geometries now. So I'm not going to formally define a reed geometry because I can just draw you a picture. So a reed geometry is just a rank 3 matroid that looks like this. So it consists of 3 copunctual lines. one of which has length exactly 3. So we call that one the intermediate line, and we usually visualize it as sitting in the middle here. And then we call the other ones long lines. So these have length at least 3. So those are the long lines. And this is the classical definition of a Reed geometry. This is all it is. In this talk, we're going to add a condition, and we're going to impose this condition that neither of these intermediate points is in a 2-point line. Okay, so that's what Reed geometry is going to mean in this talk. So Reed geometries have a lot of nice structure. So one of the first things we can observe is that these long lines have to have the same length. And the way you see that is by just taking one of the long lines. So I've drawn its points, except for the copunctual one in red. And then we just pick one of the intermediate points and consider its span with all the red points. And because all of those lines have to have length 3, they all have to hit some point on the other long line, right? So what you see is that there have to be at least as many blue points as red points. And because this red long line was chosen arbitrarily, we conclude that the long lines have to have the same length. All right, and one more structural thing about Reed geometries is that we can think of, okay, so this sentence is a little bit, maybe a bit sloppy actually, but we can think of the lines, and by lines I mean the lines through those, the 3-point lines through those intermediate points. We can think of that set of lines as decomposing into a collection of disjoint even cycles. So it should say even cycles. And to show you what I mean by this, we'll just take another look at a Reed geometry. So what am I saying? So just pick a point on one of the long lines, all right? And then pick one of the intermediate points and consider their span. So once again, that line has to hit something on the other long line, and then you just keep going in this way. So you take that next guy that you hit and consider its span with the other intermediate point, and you just keep going in this manner. Now this procedure has to terminate, and the only way it can terminate is by eventually cycling back to the first point. All right. So this is what I mean by even cycles. So what's the point of this, though? So we've seen some nice structural properties of Reed geometries, but we want this structure to tell us something in the case of representability. So what this structure tells us, particularly this even cycle structure, is the following: that if your Reed geometry is representable over a finite field F, and it contains a cycle of length 2k, then k is divisible by the characteristic of the field. All right, and this is proved in a paper of Joseph Kung from 1990. And I'm going to just really quickly sketch that proof for you. I'm going to show you how to prove this just with this small example of this 6 cycle that I've drawn. So what you do is you're representable over a field. So you start by representing this basis with these basis vectors, and then you just use row and column operations to extend this representation, like so. And then you do a bit of algebra. So what you do, and this is where the cycle structure is crucial, is you go along the lines in this cycle in turn. And going along these lines, you take each one of their determinants, which has to be equal to 0. And that gives you a bunch of equations. And I'm just going to show you them really quickly. I'm not going to spend too much time on this because the algebra's fairly easy once you get the tricks. So we have alpha 1 and alpha 2 up here. We'll call this 0 alpha 0, and we'll similarly call this 0 beta 0. And then you take determinants of all these lines in turn, and you get these equations from that. So,
sorry, when you talk about a cycle, and when you talk about a cycle here, are you talking about a cycle in the graph with the vertices on the long line? Is that what you mean by a cycle?
yeah, yeah, essentially, yes.
Or is it a Matroid circuit? I'm not.
No, it's not. Sorry, it's not a Matroid circuit. Sorry, I should have clarified my vocabulary a little more. I'm using the term cycle a bit colloquially here. So what I'm talking about is the first thing you said.
Okay.
So you think of these points on the long lines as vertices, and then you put an edge between them if the points have a long line here containing each of them in the matroid.
Okay, thanks.
Yeah, no worries. Thanks for bringing that up. So yeah, sorry. Hopefully that's clear now. Anyhow, so when you take these determinants in these lines in the matroid, you get these equations. So for this cycle of length 6, for each I modulo 3, you put these equations together and you get that alpha I plus 1 is equal to alpha I plus delta. Okay, so looking down here, we have that alpha 0 is equal to alpha 2 plus delta, and that's equal to alpha 1 plus 2 delta, and you keep applying this recursion, and eventually you get that alpha 0 is equal to alpha 0 plus 3 delta. And consequently, 3 times delta is equal to 0. Since this delta is not 0, this implies that, at least for the case of this example that I've drawn here, that if you're representable over a finite field F, then that field has characteristic 3. And this tells you quite a lot. So in particular, you look at the Reed geometry, and if you have a cycle of, well, it tells you a lot when the field you're dealing with is prime. Okay, so this is essentially why our theorem is for prime fields. When you're representable over a prime field, and you find a cycle, an even cycle, in your Reed geometry, which has to exist, you get that if the cycle length is 2k, then p divides k. K is at least p. Moreover, these lines in the Reed geometry, if it's GFP representable, have length at most p plus 1. And so putting that together, what you get is that if you have a Reed geometry representable over GFP, where p is prime, then the long lines have to have length p plus 1. In other words, the long lines are completely filled out. They're as long as they can possibly be. So that's quite a bit of structure. And this lemma is, we're going to use this repeatedly in our proof. Namely, in our proof, we're basically going to be encountering Reed geometries all over the place. And when we find one, it just means that the lines are long. They're as long as they can be. Their length p plus 1. So that's how we're going to use Reed geometries. Now, there's a couple more tools we need, namely a couple of Ramsey theorems. So just a bit of Ramsey theory for matroids. This is called the geometric Ramsey theorem. And what it says is that if we have a projective geometry of sufficiently high rank, then under any coloring of its points, we're guaranteed to find a monochromatic rank K flat. And that flat is itself, of course, a projective geometry. And we have one more Ramsey theorem here, and this one's going to be really important. So we call this one the geometric Hales-Jewett theorem, so called because you can fairly easily deduce this from the classical Hales-Jewett theorem from Ramsey theory. And this theorem is basically saying the same thing, except for affine geometries rather than projective geometries. So you have an affine geometry, so long as its rank is sufficiently large, then under any coloring of its points, you're going to get a monochromatic flat. And just like the Reed geometry thing, we're going to use this theorem over and over in our proof, and we're going to use it in kind of a special way. So there's a bit of a trick, but basically what this Hales-Jewett theorem is saying is that when you have a really big affine geometry, really high rank affine geometry, and you take a coextension, then that coextension is guaranteed to contain a high rank affine geometry. And you see this just by looking at the representation. So you have your big affine geometry sitting down here. When you coextend, the representation looks like this, and in particular, you are getting a GFP coloring of this affine geometry down here. And so by Hales-Jewett, you get a monochromatic flat under this coloring. And so you just look at that flat and you see that all of its top entries in the representation are the same. And so the thing you're getting in the coextension has to be an affine geometry itself. And you can coextend a bunch of times. You can coextend as many times as you like, so long as you've taken the affine geometry and the minor to be really big, then you can coextend a bunch of times and still find a really big affine geometry in your matroid. So that's what we're going to do. Excuse me. Okay, so now we have the tools we need to do the proof. We're not going to directly prove the theorem that I wrote down. We're going to prove something that's actually a little bit stronger. So we're going to prove this lemma, which bears some resemblance to the theorem that I wrote, but is not quite the same. So in particular, for any choice of K and R, if you take a GFP representable matroid with sufficiently high rank relative to both K and R, then you're guaranteed to find either a rank K independent flat, which is great, or a rank R affine geometry restriction, which is not quite what we want. We want to find flats. But the reason this lemma implies our main result is by that geometric Ramsey theorem I showed you. So suppose we find an affine geometry restriction. We can take its rank to be as high as we want. So suppose it looks like this, where the elements of the affine geometry are shaded. It's this shaded affine part. And then down here, we have a hyperplane. And now that hyperplane is not in the matroid. It's a hyperplane in the ambient projective geometry, whose points may or may not be in our matroid. So we can think of that hyperplane as being two-colored. right? So the shaded points are in the matroid, the non-shaded points are not, but that's a two coloring of a really big projective geometry sitting in an ambient space. So you just apply the geometric Ramsey theorem to that, and you find some monochromatic flat, i.e. you're finding a projective geometry that's either sitting entirely in the matroid or entirely outside. And so you just take its span with some point in the affine part up here, and you look at that flat. This thing down here is monochromatic, so it's either sitting completely in or out of the matroid. And in the former case, this flat is a projective geometry. In the latter case, it's affine. So that's how you get what you want. That's how we get the main theorem. Now, now I'm going to show you how we prove this lemma for the case of k equals 2, i.e. I'm going to show you how we can either find a 2-point line in our matroid, or we get an affine geometry of whatever rank we like. And the general case is a little bit more complicated than what I'm about to show you. There are some extra details that need to be taken into account, but the sketch for lines really contains all the real core ideas. So that's what we're going to go through. Okay. So the approach, so we want to find either a 2-point line or an affine geometry restriction of whatever rank we like. The approach is to kind of inductively bound line length. So you start by showing that you either have a line of length p+1 or an affine geometry. Well, that's trivial because a line of length at most p+1. I don't know if I said that. That's trivial because every line in a GFP representable matroid has length at most p+1. And then you move on to p. Then you show, okay, can I get a line of length at most p or an affine geometry restriction? And you kind of keep going in that way. So suppose that we've found some number which guarantees that if our rank is higher than that, then we either get a line of length at most L+1 or an affine geometry restriction of whatever rank we like, number depending on that. What you do is, okay, so we want an affine geometry of rank R. What you do is you contract a set of rank R. And then in that minor, you apply induction. Now, if you find, now you can assume that minor is as high rank as you want. And if you find the affine geometry restriction, then you just apply that coextension trick that I mentioned, in which case you win. So you assume that you find a line of length at most L+1 in that ultimate minor. All right, well, then you just look at the second last minor, and what you find is a flat consisting of L+1 copunctual lines. Again, you can assume that all these lines have length at least 3, because otherwise you win. And moreover, you can assume that every line in between here has length exactly L+1, because if you find a line of length at most L in the minor, then you just lift to the matroid and you get what you want. But what's the point of this? So there's no lines. There's L+1 copunctual lines here, no lines of length less than L+1. What that means is that you have essentially read geometries sitting around everywhere. All you do is pick any 3 of these lines and then choose one of them to be the intermediate line, do a restriction, and you have a read geometry. And what that means from our read geometry analysis is that, well, I've just drawn one of them, but every single one of these lines has length p+1. They're all full. But we only need to look at one of them. The reason being that that this line of length p+1, this has an affine geometry restriction. Okay, this is a rank 2 affine geometry restriction once we delete that that co-extended point. And this is, we're building up the affine geometry from here. Okay, so what you do is you just co-extend again, and you just pick one of the points in this bottom affine geometry. We know from the structure of this flat here in the bottom that this guy is contained in some line of length at most L plus length exactly L+1, and then you consider the spans of all those points with the co-extended point, and what you get is another system of L+1 copunctual lines in which there is no line of length less than L+1. And you just repeat the analysis you did at the beginning. And you conclude that this line has length p+1. So you found another full line. And now we picked this point at the bottom arbitrarily. So what we actually have is a bunch of full lines, a bunch of length p+1 lines sitting here. So now just looking at this flat spanned by the bottom black line and this co-extended point, this is a rank 3 matroid, which is GFP representable, and by construction we have p² points sitting here outside of this hyperplane. So we have a hyperplane here, this red one that I drew, and we have p² points sitting outside of it. So because this is GFP representable, this has to be an affine geometry. So by co-extending, we've found a rank 2 affine geometry. We've basically repeated the previous analysis and built up a higher rank affine geometry, and you just keep going like this until you get what you want. And yeah, that's at a high level, that's basically how we proved this. So before I wrap up, I'm just going to mention a couple consequences of our main theorem. All right, so excuse me. So one of them is what you might call kind of a conditional unavoidable flat theorem. So this says that if your GFP representable with girth at least 5, if your rank's sufficiently large, then you get a rank K independent flat. And the reason is that because the other unavoidable flats in our main theorem are full of small circuits, right? This is true of projective and affine geometries. If you just obstruct a small circuit, then you're guaranteed independent flats. And actually, yeah, right. So I've written girth at least 5. You need that for GF2, but actually, for any other finite field, girth 4 is enough. But anyhow, I think this result's kind of noteworthy because I think it's kind of surprising. So if you think about small circuits, right, 3-point lines, these are the smallest possible obstructions to getting an independent flat. And so what we have here as a consequence of our theorem is that if you just forbid like the smallest possible obstructions to independent flats, then you're guaranteed to find independent flats of whatever rank you like. So that's something that I find kind of surprising, at least. And then one more consequence here is a Ramsey theorem for GFP representable matroids. So we saw a couple Ramsey theorems for matroids already for projective and affine geometries. But in fact, our theorem tells us that we get a Ramsey theorem for general GFP representable matroid. So in particular, you take a GFP representable matroid with really, really high rank, then under any 2 coloring of the points, or any L coloring actually, you're guaranteed to get a monochromatic rank K flat. And the reason, and to show this, you just apply our theorem. So you color your GFP representable matroid by the theorem. If you have an independent flat, then you just color it by majority, just take the biggest color class and you get what you want. And then if you get an affine or projective geometry flat, then you just apply the earlier Ramsey theorems and just look at those, use those Ramsey theorems on whatever flat you have, and you get the monochromatic flat. Okay, so that's those are the 2 kind of main corollaries I wanted to mention. And so finally, right before I wrap up, I'll just address James's question from before. So our theorem is for prime fields. What about prime powers? What about general finite fields? And yeah, so James guessed it that what you might try to do is show that if you're representable over a prime field, then the unavoidable flats are either independent flats or an affine or projective geometry over the base field. Okay, and so the reason we look at the base field here is just because of representability and nested subfields. So you might guess, oh, okay, so we want to generalize the theorem. You know, our affine or projective geometries over GFQ unavoidable. Well, that can't be true because, so if you were just talking about GF4, you could just take a binary projective geometry, which is representable over GF4, but clearly doesn't contain an affine or projective geometry over GF4. So that's why we talk about the base fields here.
So Matt,
sorry.
You could actually be a projective geometry over GF4.
Okay, GF8 then.
Your matroid could be a projective geometry over GF4, so this wouldn't hold for those. So you have to take over arbitrary subfields.
Isn't that what I said? Or did
your conjecture, what you wrote as a conjecture, doesn't match what you said.
Oh,
you're saying you get a flat that is over the base field, but you might be a projective geometry over the actual field, and then this wouldn't be true.
Oh, right.
Needs to be for every subfield. You need to look at the affine and projective geometries.
Yes. Sorry. My bad. That's correct. So affine geometries over a subfield is what I should have written. I'm sorry. I wrote this slide this morning and obviously wasn't thinking clearly. Okay, anyhow, but yes, so this is the future work on this problem, and so Jim and I have teamed up with Peter to work on this, and yeah, that's all I have to say. Thanks everybody for coming and for listening.
Thank you, Matt. Are there any questions?
Yeah, I thought it was a nice talk. Thank you, Matt. I was just, you said the Sylvester-Gallai theorem says that you've got at least one 2-point line. What can you say about how many 2-point lines you have to have? I mean, do you have to have at least the rank, or is it, what can you say about that? Anything?
Yeah, you can say, you can definitely say some things. I actually don't know about the rank, but you can bound it in terms of the number of elements in the Matroid. So this was a conjecture, I believe, of Dirac, that you could get. So if n is your number of elements, then you can get n over 2 2-point lines for a rank 3 real representable Matroid. That's not actually true, but it's true for n sufficiently large, and that was proved by Ben Green and Terence Tao.
Okay.
Yeah. So that stuff's pretty interesting as well. I haven't given too much thought about the number of these things.
So I assume they're using quite sophisticated tools then, given the players, Green and Tao, at least, you know.
Yeah. It's a long paper, which I've never read, but there are more elementary ones, and I don't know the citations off the top of my head, but you can still get pretty good bounds along those lines by simpler methods. But yeah, the Green and Tao one is pretty tricky, I think.
Okay.
Yeah.
Thank you.
Are there any other questions?
I had a question. So I'm new to Matroid theory. Can you explain what is an independent flat? I know the definition of flats only.
Oh, okay. Well, I just mean, so you know the definition of flats only. So, well, flats are harder to explain. Independent flat, I just mean a flat which is itself an independent set in the Matroid.
Okay. Thank you.
Are there any more questions? If not,
All right,
then
I'm going to ask another question. These numbers, I assume the numbers are huge and they come from the Hales-Stewart theorem and so on. So you're not, do you know, I mean, can you say anything at all about the numbers, how big the rank has to be?
I've never bothered to try.
That big,
it's really like even just for that line. I mean, for the proof I just outlined with the lines, it might not be too difficult to say something about the numbers. It wouldn't be immediate, but they're pretty nasty because so how many times are you applying the Hales-Stewart theorem there? I guess L minus 1 times, I think. Yeah, and that's like cumulative in terms of the numbers. So they're pretty bad, and you're doing it way more times when you're dealing with higher rank independent flats.
Yeah.
You should be able to get some lower bounds from probabilistic stuff that show you that the numbers can't be that nice, even in the best case.
Yeah, that's a good point.
They
I've-
won't match the upper bounds, but
Yeah, still could be interesting. I've never thought about that. Actually,
Yeah, theorem-
before we came up with this approach, we just had a proof for binary, and so we knew how to do binary for a while, and that proof actually used the density Hales-Jewett theorem, where things would have been even worse.
the binary version of that's not so bad. There's a result of Bonin and Chin, which makes it it makes it something that you could write down, I think.
Oh, okay.
We did iteratively use the hypergraph Ramsey theorem before we did the
Right.
Yeah.
Hales-Jewett, so it was actually pretty bad.
Yeah, with that proof, it was really nasty. Yeah.
Maybe I'll say thank you, Matt, again, and I'll wrap up the recording there.